Yes, start பண்ணிடலாம்.
A warm good afternoon to one and all gathered here. Let us begin today's program with silent prayer. Thank you, everyone. A warm good afternoon to one and all once again. I now invite our HOD, Professor Dr. A. Nagarajan, to deliver the welcome address. Sir, please.
First, I welcome Dr. R. Kala, Professor and Head of the Department of Mathematics, Manamnim Sudarna University. And when I approached her, he readily accepted to deliver lecture for our FDP program. Thank you, ma'am. And I wish to introduce her. She has completed a MSc, MPhil, MAth, PhD degree. And she took 3rd rank in BSc Mathematics and 8th rank in MSc Mathematics and 2nd rank in MPhil Mathematics. And all the 3 are from MK University. See, nowadays we are only having MS University, and before 1990, Madurai University means all Madurai district and as well as Tirunelveli, Thoothukudi and Kanyakumari and Virudhunagar, everything is under the control of Madurai Kamaraj University. So in that she took ranks, and her area of research is graph theory. And her research experience is 25 years and 29 years, and the teaching experience is 25 years. She completed 11 students as a guide and 16 students as a co-guide, and the number of scholars pursuing research as a guide 6, and the number of scholars pursuing research as co-guide as 4. Number of articles published in refereed journal is more than 130, and the number of books published is 3, and number of conferences attended is more than 115, and her Height index score is 13, and the I-10 index score is 17, and number of citations is 493. So with this introduction, I welcome Dr. Kala Madam, and I ask her to give their valuable lectures. Thank you.
Thank you, sir. Kala ma'am,
so, good evening, everyone.
Sorry, ma'am. Sorry to disturb.
Yeah. Okay, ma. You carry on.
I was just going to invite you, ma'am, on behalf of everyone. I take pleasure in inviting you to give the address to the participants, your address to the participants. Thank you, ma'am.
Thank you, ma. Thank you. So, at the outset, let me thank the management, the secretary, principal, and the head of the Department of Mathematics of V.O.C. College for giving me this opportunity. And thanks, sir, for the nice introduction given.
Thank you.
So let me start sharing the screen. Jackson sir, and the enable பண்ணணுமோ sharing.
Jackson.
Sharing option
No ma'am, you can share. It has been enabled already.
அந்த விண்டோவே வரலையே சார், ஷேர் விண்டோவே.
மேம் இதுல அந்த மாதிரி ஆப்ஷன்ஸ் எதுவும் இல்ல மேம், நீங்க ஷேர் பண்ணலாம்.
ஓபனே பண்ண வேண்டாமா
மேம்? நீங்க உங்களோட இதுல பாத்தீங்கன்னா கீழ ஒரு ஆரோ மார்க் போட்டுருக்கோம், அப்படி இல்லாட்டி மோர் ஆப்ஷன்ஸ் போனீங்கன்னா தெரியும். ஒரு ஆரோ மார்க் போட்டு ஷேர்
கிளிக் பண்ணா
அதுல தெரியல சார்.
கிளிக் பண்ணா எதுவுமே வரலையே சார்.
அந்த ஆப்ஷன் தெரிய மாட்டேங்குது. பிரசன்ட் நவுன் இருக்கு மேம். 5th ஐகான் பாத்தீங்க அப்படினா
எதுலமா
5th ஐகான், இந்த கைக்கு அடுத்து ஹேண்ட் சிம்பிளுக்கு அடுத்தது பிரசன்ட் நவுன் இருக்கு.
அது வந்து எனேபிள் ஆகல. அதாவது டிம்மா இருக்கு. இட் இஸ் நாட் எனேபிள்ட்.
Okay.
நீங்க அந்த
ஒரே
ஹோஸ்ட்ல ஏதாவது பண்ண வேண்டியிருக்கும்னு நினைக்கிறேன் சார்.
ஓகே மேம், நான் அதை செக் பண்றேன்.
அந்த அப்வர்ட் ஆரோ வந்து எனேபிள் ஆகாம அது மட்டும் டிம்மா இருக்கு.
மேம் ஷேர் ஸ்கிரீன் நான் எல்லாருக்கும் எனேபிள்ல தான் வச்சிருக்கிறேன்.
என்ன ப்ராப்ளம் தெரியலையே.
செக் பண்றேன்
திரும்ப
மேம்.
வெளியே போயிட்டு உள்ள வரவா சார்?
ப்ளீஸ் மேம், ப்ளீஸ். So respected participants, please stay tuned. Ma'am, is it okay now?
Yeah, I think now it is enabled. Let me start.
Please ma'am.
சார் அந்த யுவர் என்டையர் ஸ்கிரீனை பிரஸ் பண்ணவும் இது வந்து டிசேபிள் ஆகுது. என்ன ப்ராப்ளம் அது?
இது மேம்
அந்த அப்வர்ட் ஆரோ இருக்குல்ல சார்? அதுல யுவர் என்டையர் ஸ்கிரீனை நம்ம கிளிக் பண்ணும்போது இது டிசேபிள் ஆயிருது.
நோ இஷ்யூஸ் மேம். ஒன்று பண்ணலாம். நீங்க உங்களோட இதை வந்து மெயிலுக்கு அனுப்புறீங்களா மேம்? நான் இங்க இருந்தே ஷேர் பண்ணிடுறேன்.
ஓகே.
சஃபினா மேம்,
Yes, sir.
உங்களோட மெயில் ஐடி கொடுங்க மேம். பீயிங் த மாடரேட்டர், மேம் உங்களுக்கு ஷேர் பண்ணாங்கன்னா நீங்க உங்க எண்ட்ல இருந்து ஷேர் பண்ணிருங்க.
Okay.
உங்க சாட் பாக்ஸ்ல உங்களோட மெயில் ஐடி சாட் பாக்ஸ்ல டைப் பண்ணி.
சொல்லிருக்குமா? நான் டைப் பண்றேன்.
SAFINANERR.
SAFINA at
NERR@gmail.com.
SAFINARR
NERR. சாட் பாக்ஸ்லயும் போட்டிருக்கேன் மேம். சஃபீனா NERR. SAFINANERR. ஆமாம். Just a minute.
I have sent ma. See whether you have received.
Yes, ma'am, please. I haven't received it yet, ma'am. Just a minute. Ma'am, can you please send it again?
Yeah, I have sent again. It is from Karthi PYI 91. The mail ID will be Karthi PYI 91.
I've
Ma'am,
posted
check
my
your
mail ID
spam
in the,
also.
yes, I just did, but I didn't get it yet. Can you please verify the email ID in the
No,
chat box, ma'am?
I've just copied and
Oh,
pasted
okay.
there.
Okay, ma'am. Okay.
இன்னும் வரலையா?
வரல மேம், என்ன பிரச்சனை தெரியல.
No issues, ma'am.
Yes, please, sir.
மேம் வாட்ஸ்அப்ல அனுப்ப சொல்றீங்களா மேம்?
Anything is fine. ஒரு நிமிஷம் மேம், I'll send my number. Maybe if my connection is very weak and then I doubt the presentation will
எனக்கு
go
அனுப்புங்க, நான்
smoothly.
அனுப்பிடுறேன்.
அனுப்புறீங்களா? சரி. உங்களுக்கு அனுப்பிட்டேன் சார்.
சஃபினா மேம், இஃப் பாசிபிள் ஒன் செகண்ட் ஸ்பாம் செக் பண்ணிக்கிறங்க, பிகாஸ் மேமோட மெயில் வந்து நியூ மெயில்னால உங்களுக்கு அப்படி இருக்கலாம்.
Okay, sir.
Sorry, respected Kala ma'am. Sorry for the inconvenience. And respected participants, please be patient.
நாகராஜன் சார், நீங்க எனக்கு அனுப்ப முடியுமா சார்?
இல்ல, இன்னும் வரல, மேடத்துல இருந்து வரல.
வரல. சரி சரி.
என்னோட நெட்வொர்க்ல தான் எதுவும் ப்ராப்ளமான்னு தெரியல.
Yes ma'am, yes.
இன்னும் வரலையா சார்? உங்களுக்கு வரலையா?
வரல மேடம். நீங்க எனக்கு வாட்ஸ்அப் தானே அனுப்பியிருக்கீங்க மேடம்?
இல்ல சார், மெயில்.
மெயிலோ? சரி.
ஆமா, மெயில்.
மெயில் பாத்து. மெயிலையும் வரலையே மேடம்.
Ma'am, I got your mail.
Okay.
PDF file are
PDF.
presentation.
PowerPoint.
Okay. Shall I share, ma'am?
Yeah.
Yes ma'am. Yes, is it visible? It is visible now ma'am.
Yeah.
Make it as slideshow.
I've made it. Is it visible properly now?
You can close that left slides.
Yes ma'am. Make it as slideshow.
இல்ல ஸ்லைட் ஷோ மாத்திட்டேன் சார். உங்களுக்கு விசிபிளா இல்லையோ?
இல்ல.
மேபி ஒரு 10 seconds டிலே இருக்கலாம் மேம். இது வரைக்கும் இது இல்ல, இப்படியே தான் இருக்கு. Shift plus F5 or on the 7th option slide show.
ஸ்லைட் ஷோ இருக்குல்ல மேடம்,
ஓ வருதா சார்?
வரல ஸ்லைட் ஷோலே இல்லையே.
I'll share my entire screen and then change. அப்போ change ஆகுதா பார்க்கலாமா? 1 minute.
இல்ல வியூல இருக்கு, ஸ்லைட் ஷோல இல்ல.
அது சரி, எனக்கு ஸ்லைட் ஷோவா இருக்கு, பட் அது ஷேர் ஆகும்போது வர மாட்டேங்குது. 1 minute, just a minute. இப்போ தெரியுதா சார்?
Yes, ma'am. Yes, ma'am.
ஓகே
Okay. So
Please,
thank
ma'am.
you. Thank you, everyone. And sorry for the inconvenience. So
No problem.
okay, title of my talk is Some Conjectures and Open Problems in Mathematics. Actually, such conjectures and open problems, they give an insight into certain mathematical ideas, and it creates an interest among students to work in that particular problem, so that in some time or other they would solve and get fame and bring dollars to that institution. Okay, so next one. So let me start with a tribute to these two persons who received the Abel Prize this year. So the first one is a graph theorist, and the second one is from computer science department. The first one is Lovas, and the second one is Evingston. Okay. So next slide. So this is actually an introduction or a tribute to the two mathematicians, I can say, and then I will go into my topic. This Abel Prize was established in the name of the mathematician who lost his life at a very young age, and that is Abel. Okay. And it was established on 1st January 2002. Actually, as we know, this mathematics has no Nobel Prize. So equivalent to the Nobel Prize, we have this Abel Prize, as well as there is another medal called Fields Medal. And the purpose is to award this for outstanding scientific work in the field of mathematics. And the prize amount is 7.5 million Norwegian dollars. And it was awarded for the first time in June 2003. Next one, ma. Next slide. So the organization which creates this award, that is Norwegian Academy of Sciences Letters, and that has appointed an Abel committee, which consists of 5 mathematicians, to review the nominated candidates and to submit a recommendation for a worthy Abel laureate. And because of COVID, last year this award was not given. So this time it was given to 2 mathematicians, Lovis and this computer science person. Okay. Next one, ma. So this is of course the 2 persons, and every time when they give an award, they give a citation. So this time the 2 persons are Laszlo Lovas, and the another one is A.V. Vigderson of USA, and the citation is given in the next page. So in the next slide. Okay, so the citation is like this. This Abel Prize is awarded to these 2 persons for their foundational contributions to theoretical computer science and discrete mathematics, and their leading role in shaping them into central fields of modern mathematics. Okay. So next you have, of course, this Abel. He died when he was 26. But in that 26 years, he has given so many things. He gave the first proof of the general binomial theorem, okay, and so many other work. And next one, you have the picture of Abel. So with this as a tribute to Abel and also to both Lovas and Evingston. Okay, let me just next slide, ma. Next slide. Okay. So this is of course the only Indian who has been awarded Abel Prize, that is Srinivasa Varadhan. Though an Indian, it is of course he is a foreign citizen of foreign USA. He's an Indian mathematician awarded this 2007 Abel Prize, and the only Indian who has been given this award. And it was given for his fundamental contributions to probability theory, in particular for creating a unified theory of large deviations. Okay. So this is Srinivasa Varadhan. So let me start with my first conjecture. Actually, I will not enter into any deep mathematics. I'll be just giving the history of the conjecture, whether it is solved or not, and what are all the developments that has been done based on the conjecture. And of course, I'll explain the conjecture. Okay. See, this is, of course, a very simple problem, but mathematicians say that it is a very dangerous problem. Even mathematicians advise that please don't work on this problem because they believe that it will take the entire lifetime of a person who works on it, and even then he may not succeed. So it is called as Collat's conjecture, and common name is 3n+1 problem. And all other names are Ulam conjecture, Kakutani's problem, Syracuse conjecture, Thwaites conjecture, Hazy's algorithm, everything refers to this same conjecture. And the mathematician Paul Yerdas, he even made a remark that mathematics is not yet right to answer such questions. So it is a very simple problem, but only of course, I can say that not much has been done in the problem because people find it very difficult to take the first step itself into this. And it has been said that this problem was posed by the Russia to reduce the speed of research of USA. Okay, and many mathematicians, they say that youngsters, you please don't work on this conjecture because it may spoil even your career. You may not be able to proceed further, but of course your lifetime will be lost in solving this problem. Okay. So let us go into the problem. Next slide, ma'am. Okay. So of course, this is the way in which I'll be presenting this conjecture, the statement, and then for some numbers, you can see how it works. Actually, I thought of doing it using the whiteboard, but now I couldn't do it. But anyway, I can manage. So next slide, next. Okay. So this is the conjecture. Even you can give it as a game to your kids. So you're going to do something in an arbitrary positive integer. So take any positive integer. You have to do two things. You have to look at the parity of the integer. If the integer is even, you have to divide it by 2. And if the integer is odd, you have to triple it and add 1. Okay, so that is 3n+1. That is the problem. So you have a function f defined by f of n is equal to n by 2 if n is even, and 3n+1 if n is odd. Okay. So you can take your number, the number with which you start, that you can take as the height above the ground in meters, anything you can take. And you are going to perform this operation. So when the number is even, you will come down because it is n by 2. So if you look at the graph in which you are getting your numbers, if the number is even, you will come down. But if the number is odd, you will move very long, very up. Okay. So that whenever you get an even number, you will come down, and whenever you will get an odd number, you move high, and so on. It goes on like this. So you are getting a sequence of numbers. Okay. And the conjecture says that it will end up in 1. Whatever larger number you take, finally you will end up with 1. That is the conjecture. So you are going to form a sequence of numbers by performing this operation repeatedly. You can start with any positive integer. If it is even, divide it by 2. If it is odd, triple it and add 1. Okay. So next one, Safina. So for example, if I take n equal to 6. So I start with x6. 6 is even. So divide by 2, 3. So I come down. So I can say that from a height of 6 meters, I come down to a height of 3 meters. Now 3 is odd. So I multiply it by 3 plus 1. So I get 10. So I have come down from 6, but I move up to 10. And then 10 is even, 5. So you go on doing this. Finally, after 8 steps, and in the 9th step, I get 1. And once you get this 4, 2, 1, that forms a loop because 1 is odd. So I get 4. 1 into 3 plus 1, I get 4. 4 is even. So I get 2. And 2 is again even. So I divide it by 2, I get 1. So this 4, 2, 1 will be going on repeatedly, forming a loop. It will be going on. The sequence will be going on endlessly. Okay. So the process will eventually reach the number 1, regardless of what positive integer is chosen initially. That is the problem. That is the conjecture. And you can see that the numbers behave in a very random way. There is nothing could be found out. No symmetry or anything could be found. You can see that. Just next one. If you take n equal to 11, you get the sequence. Okay. And the numbers in the sequence that you get, that is by performing n by 2 and also by performing 3n plus 1, that sequence of numbers, they are called as hailstone numbers because they move down and then they move up, again move down and so on. So all the numbers in the sequence that you get are called as hailstone numbers. So you have started with 11 and you have reached 1, maybe in the 14th step, if I am correct. Okay. So next one. So you can, when n equal to 26, if I take, I can see that I will reach the 1 in some 11 steps. Okay. But the next number, that is if I take n equal to 27, you can see the sequence. This is how the sequence goes on. And then finally, yes, next page. Okay. Finally, you will be ending up with that 4, 2, 1 in 111 steps. So for n equal to 26, just in 10 steps, you'll get the answer. But for n equal to 27, you take 112 steps. And your actually the highest number that you climb up is 9232. That is the largest number. And you can see that it is even greater than Mount Everest, the height of Mount Everest. Provided you take this number as the height above the ground in meters. If I take it like that, then I get the number 9232 if I start from 27. And this 9232 is higher than the height of Mount Everest. Okay. So next one. Okay. So that is of the 3n plus 1 problem. The thing is, even so many people have worked, but they couldn't find anything common, because whenever you want to solve some problem, we'll be starting with examples. And once you do some 10 or 20 examples, something will strike in your mind. That is, you can find out some similarity. You can see that it will be like this. You can view something. You have, but in this problem, nothing could be got because there is no symmetrical anything. Nothing is symmetrical or no common things. Every integer behaves in a very different way. So once you start, you have to go on finding it for numbers. And for, of course, for all the numbers they have checked, they found it to be true. But still this 3n plus 1 problem is still an open problem. And as many mathematicians advise that, please don't enter into the problem because it may be a barrier to your career. That is what they say. Okay. And the second one is Goldbach's conjecture. This is again a very simple conjecture, but you can see that how many centuries it has been passed till the conjecture is not solved. Okay. So Goldbach, he posed this conjecture in the year 1742 to Euler. And the thing actually, normally in olden days, we have some conventions. Okay, like that, he had a convention that 1 is a prime number. So with that convention in mind, the original conjecture was given like this. Every even integer greater than 2. Okay, can be, because 2 cannot be written in that way. So every even integer greater than 2 can be written as the sum of 3 primes. That was the original conjecture given by Goldbach. But of course, he had a convention that 1 is a prime. But of course, Euler, he re-expressed it as every even integer greater than 2 can be written as the sum of 2 primes. Because 1 cannot be included. So he reduced that 3 into 2. And you can check, of course, every even integer greater than 2. You can see that it can be written as the sum of 3 primes. If you start with 18, I can write 5 plus 13. Also, of course, can be written as 7 plus 11. So those 2 primes would form the sum of that integer that is called as Goldbach partition. Okay. Next one. Okay. And once in a Congress of Mathematics, okay, one mathematician said that it appears to be as simple as it is difficult, because anyone can understand, even a school student can understand the problem. Normally, some conjectures, they are very difficult even to understand. If you have that, if you go through that Riemann hypothesis and continuum hypothesis, In order to understand the conjecture itself, we need so much of mathematics. But here it is not like that. A very simple problem. Even any school student can attempt that particular conjecture, but still it is unsolved. For centuries, it remains unsolved. And the mathematician Faber, in order to attract people towards this problem, he offered this amount, that is $10 million for anyone who solves the problem, but he fixed a date. It is from March 20, 2000 to March 20, 2002. So he gave 2 years time, but no one solved it. And so the amount went unclaimed, and still it is an open problem. And normally whenever you have a conjecture, instead of solving the conjecture as a whole, either people look at equivalent things, because sometimes it may be easy to approach a sub problem in using some other tools. So people started weakening the conjecture, and so many things are done. And one weak Goldbach conjecture is this one. All odd numbers greater than or equal to 9 are the sum of 3 odd primes. Okay, it is not all the even integers. All odd numbers greater than or equal to 9 can be written as the sum of 3 odd primes. So this is called as weak Goldbach conjecture. And after 2.5 centuries of making this conjecture, this was proved by Helfgott. That is during 2013 and 2014. See, whenever people prove something, it should be presented to the mathematical community. So they should be, of course, they should accept it as a logic without any logical errors or anything. So it was presented in 2013, some flaw was found out, and then he corrected it. And in 2014, it was accepted. So the weak Goldbach conjecture that was proved by Helfgott. Okay. So next one. This is a stronger version of that weak conjecture. That is every odd number. Here you are including 7, greater than or equal to 7, but it is not 2 primes. It is a sum of a prime plus twice a prime. Okay. And this, of course, this conjecture is called as Levy's conjecture. So 13, you can write it as 3 plus 2 into 5, and 19, 5 plus 2 into 7. And this conjecture, of course, still it is open. It has been verified up to n less than or equal to 10 power 9. But it is not solved. Okay, it is still an open problem. This next one. Okay. An equivalent statement of this conjecture is this. Given any, that is Goldbach conjecture, given any positive integer m, that is an even number, 2m. So there are primes p and q such that phi of p plus phi of q is 2m. Phi is the Euler's phi function. That is, it gives the tangent function, the number of integers less than n and relatively prime to n. So that is Euler's function. Of course, you have phi of p is p minus 1. Okay. So it is phi of p plus phi of q is equal to 2m. So it is enough if you find p and q satisfying this equation. That is an equivalent statement of this Goldbach conjecture. See, whatever problem you give, you can approach that problem through different areas. Suppose if I have a problem in number theory, I can approach it using tools of algebra or using tools of combinatorics. Anyway, I can approach. So this is another way of defining it using Euler's function. Okay. And of course, there are many other variations, equivalent forms of Goldbach conjecture. That is, every even number greater than or equal to 6 can be written as the sum of 2 odd primes. Okay, every even integer greater than 17, that is the sum of exactly 3 distinct primes. All of them are equivalent versions, but the problem is unsolved. Goldbach conjecture remains unsolved. Okay. And this, the person Levy, he in ICM, you know, the International Congress of Mathematics, there he presented 4 problems in prime numbers, and one of them is this Goldbach conjecture. Okay, okay, my next one. So this is called as twin prime conjecture. That is the 2 numbers, maybe definitely 2 consecutive numbers will not be prime, because either one of them will be an even number. Exactly, one of them will be an even number. So the conjecture says that there are infinitely many primes p such that both p as well as the next consecutive number, that is p plus 2, both of them are prime. So they are called as twin primes. So a number which is a prime number and the next consecutive number, that is p plus 2, should also be a prime number. So such numbers are called as twin primes. So 17 and 19 are found to be twin primes. So the difference between the two consecutive numbers is just 2. Difference between two consecutive numbers is 2. Okay. So that is the conjecture. So the conjecture says that there are infinitely many such primes. But people, they have found out only 15 such pairs. But it is still an open problem. Zhang proved that the gap is bounded by 70 million. That is, instead of taking consecutive, instead of taking the gap to be 2, he took the gap as 70 million and he proved that there are infinitely many primes P. So P plus P and P plus 70 million. That is what he considered. And he said that he has proved that there are infinitely many primes P such that both P and P plus 70 million are primes. Okay, that has been proved. And later that theorem was improved. The gap is reduced to 246. And then again, another mathematician proved that the gap could be reduced to 6. So this is the result that is available now. So there are infinitely many primes such that P and P plus 6, both of them are primes. But the conjecture is P and P plus 2. Okay. So that still remains unsolved. So next one. Okay. And Chen, he proved that instead of taking both of them to be, that is P and P plus 2, both of them to be primes, he took one of them as a prime and another one as a semi-prime. So there are infinitely many primes P such that P and P plus 2, okay, both of them are, one of them is a prime, either of them is a prime or a semi-prime. So that has been proved. And Legendre's conjecture says that, does there always exist at least one prime between consecutive perfect squares? You know a perfect square, n square. Okay. So n square, the consecutive perfect square is n plus 1 the whole square. So do you have at least one prime between two consecutive perfect squares? That is Legendre's conjecture. So that is proved up to 2 power 64. It has been proved up to 2 power 64. And the mathematician Ingham, he proved that it is true. Instead of taking n square, he took n cube. So there is a prime between n cube and n plus 1 the whole cube for large n. That has been proved. But so that is for cubes. Okay, it is open for perfect squares. Okay. So next one. Okay. So primes of the form n square plus 1, they are called as near square numbers. A number which is of the form, because it is not n square, it is n square plus 1. So it is called as near square numbers. So the question is, are there infinitely many primes of the form n square plus 1? Okay. And Ivanik has proved this theorem, but not for all numbers, for numbers with at most 2 prime factors. Okay, for that particular numbers he has proved. And all these problems, okay, the 4 of these problems, they are given by Landau in ICM. ICM means that is the International Congress of Mathematics. So for every 4 years, they conduct that particular congress throughout of course, it is a universal program. Mathematicians from different parts of the country, they will assemble in one place. And only in this ICM, the Fields Medal is given. So I think it is in 2017, in last one is 2018. And now it was planned in Russia, that is during the month of July. But because of the war, it has been made online. Okay. The last one was, that was in 2018. Okay, that is in Rio de Janeiro. Okay. Next one. And it is in this ICM that Fields Medal and many other medals are given. And the next conjecture is Hadamard's conjecture. The conjecture states that there is a Hadamard matrix. Let me explain what is an Hadamard matrix in the next slide. So the conjecture says that there exists a Hadamard matrix for n equal to 1, for n equal to 2, and also for every positive multiple of 4. That is a number of the form 4k, where k greater than or equal to 1. So that is the conjecture. So you have an Hadamard matrix. So that is a square matrix. So the order is n by n. Okay. So for n equal to 1, you have a matrix. For n equal to 2, you have a matrix. And for every positive multiple of 4, you should have the matrix. Okay, that is the conjecture. So Hadamard matrix is a square matrix. The condition is, of course, the entries are 1 and minus 1. Whatever two adjacent rows or two adjacent columns you take, half of the adjacent cells should have the same sign and half of them should have different sign. That is, half of them should have +1 and half of them should have -1. So the entries are +1 and -1. So whether you take two adjacent rows or whether you take two adjacent columns, okay, half of the adjacent cells should have the same sign and half of them should have different sign. Actually, this Hadamard matrix, it has some sort of application in pavements. That is when you fix the tiles in the ground. Okay. So suppose if I take a cell with +1 as black and a cell with -1 as white, then I can say that n into n minus 1 by 2 cells should be white and n into n plus 1 by 2 black. Because it is the n by n matrix, so I have n square cells. So n into n minus 1 by 2 should be white and n into n plus 1 by 2 should be black. So that is the Hadamard matrix. And you can see that, of course, if you take Hn and Hn transpose, you would get n into the identity matrix. That is the n by n identity matrix. Next one. Okay. So from this Hadamard matrix, you can draw a Hadamard graph. So for every entry for every n, I have 4 n vertices. Okay. So a n Hadamard graph means the graph contains 4 n vertices. So the vertices I plot as Ri plus, Ri minus, R representing row, ith row. Ri means ith row. Okay. And then Cj, the jth column, Cj plus and Cj minus. So for every row you have 2 vertices, that is Ri plus and Ri minus. So there are n rows. So I get 2n such vertices. And also there are n columns. For every column you have Cj plus and Cj minus. So in total you have 4n vertices. Okay. Corresponding to every row and every column, you have 2. And then how do you make them adjacent? So if the entry is +1, I draw an edge between Ri plus minus to Cj plus minus. Okay, all of them are made adjacent. And if it is -1, that is all of them in the sense correspondingly. Ri plus to Cj plus and Ri minus to Cj minus. And if the entry is -1, you draw Ri plus to, you join Ri plus to Cj minus and Ri minus to Cj plus. Okay, that is how you draw the graph. And you can see that if n is equal to 1, that is my matrix will have only one entry. So my graph will have 4 vertices. So you can see that your graph is 2k2. And if n is equal to 4, your graph is the cycle on 8 vertices, that is E8. Okay. And given the 2 Hadamard matrices Hn and Hm, you can construct Hn, m. That is obtained. So Hn and Hm will be of order n by n, m by m. So you have n into m cross n into m matrix. Okay. It is obtained by replacing ones in Hm by Hn. So in Hm, you will have +1 as well as -1. Replace all +1 by Hn and all -1 by -Hn. Okay. In this way, you get Hn, m. So from H2 and H2, you can get H4. And from H4 and H4, you can get H16 and so on. Okay. So next one. So of course, I have not drawn that matrix. So if you take this as H2, okay. So having 2 rows and 2 columns. So you have 1, 1, -1, -1, +1. Okay. So whatever 2 rows and 2 columns adjacent, of course, there are only 2 adjacent rows. You can see that 2 things, 2 of them, one is same, +1 and +1. Another one is different. One is +1, another one is -1. So the signs are different. If you take the 2 columns, again, you can see that signs are different. Okay. Now, how do you get H4 from H2? So H4 is H2, 2. So you take the first one, replace it by H2. Take the second one, replace by H2. Minus 1 is replaced by minus H2. And then last one is replaced by H2. So you get another matrix H4 with 4 rows and 4 columns. Okay. So this is how you go on construct Hadamard's matrices. And people say that it exists. So given an N and M, of course I can construct, but I have to prove the general existence. And Paley, he has proved partially, that is for N, which is of the form, of course, a multiple of 4 and of this particular form, 2 power E into P power M plus 1, where E is any positive integer. And of course, M is also a positive integer. But here you should have a power of a prime, P power M plus 1. So the number should be of this particular form. So if the number is of this particular form, he has given a general way of constructing this Hadamard's matrix. So that is a partial proof of the problem. Okay, that is Paley's theorem. Next one. Okay. Of course, you know Sudoku square because many people are interested in completing the square in newspapers and in magazines. So how many different Sudoku squares of size n by n are there? Okay. So of course, that problem is also, that number is also has to be found out. So the given number, it is the number of valid 9 by 9 Sudoku squares. So the problem is to find a formula for the general n. Okay. Yes, ma, next one. Okay. See, Hilbert, he presented some 23 problems in the International Congress of Mathematics, that is in the year 1900. Okay. And also these problems, they were published as open problems in the year 1902, that is in the Bulletin of American Mathematical Society. And the first among these 23 problems, that is the third problem, which is solved. Okay. And of course, so many other things remain unsolved. The Riemann, of course, the first thing is third, but of course, some problems are solved. And the 8th problem is Riemann hypothesis. Okay. Riemann hypothesis deals with roots of the Riemann zeta function. Actually, I will be giving you the statement, but it is not so easy. That is, understanding the problem itself needs some basic idea of all the other things. It is not as easy to understand as you could understand Goldbach conjecture. Okay. So the first problem is continuum hypothesis. See, once people asked, the press reporters, they asked Hilbert, suppose if you are born after 2000 years, what will be the first question you ask? And Hilbert said that, has someone solved continuum hypothesis? That will be my first question, he said. So it is open for a very long time. Okay. Actually, in order to understand continuum hypothesis, you need to understand you need to have some basic idea about the Aleph naught and Aleph 1, because normally we don't study them in our syllabus. So the hypothesis says this. Let me just give it. Okay, Aleph naught means, when we were students, we studied a paper called History of Mathematics, where we study this Aleph naughts and then the formal logic and then the Zermelo-Frankel axioms. Everything would be taught there, but now you don't have such a paper in our syllabus. So all of us know about cardinality, but we speak of cardinality only for a finite set. We never ask about cardinality of the set of integers or of real numbers, but such things also exist. Okay. So what about the cardinality of the set of all integers? That was the first question. You know, set of all integers is an infinite set, and we are not used to, because our mindset is cardinality means number of elements. So how could I count the number of elements in Ez? So it is, of course, just by, as you do for a sequence. Okay. So the cardinality is given as Aleph naught, Aleph 0 or Aleph naught. And then if you take the set of all the subsets of Ez, that is power set of Ez. And you know, whenever a set is of cardinality, cardinality 2 power n. Okay. So this set of all subsets of Ez, that will have cardinality 2 power Aleph naught in the usual sense. And this 2 power Aleph naught is called as Aleph 1. And the cardinality of R, that is the set of all real numbers, that is Aleph 1. Okay. So you know Aleph naught, that is the cardinality of set of integers, and Aleph 1, that is the cardinality of the set of real numbers. So continuum hypothesis says that there is no set whose cardinality is strictly between Aleph naught and Aleph 1. That is the conjecture. Okay. So there is no set. The cardinality of the set should be strictly larger than Aleph naught and strictly lesser than Aleph 1. So that is the conjecture, which still remains unsolved. Okay. But people proved that, see, originally, when we had the original axioms, I can say, there were so many paradoxes and so many other things. So people found it very difficult to manage with those axioms. So the new axioms, namely Zermelo-Fraenkel axioms, they were found out. Okay. But now it has been proved that using that ZF axioms, one could not solve continuum hypothesis. So we may have to build up some more axioms to solve this continuum hypothesis. But the problem is now you can understand. So there's a set of integers and the set of real numbers. Set of integers having cardinality Aleph naught. Set of real numbers having cardinality 2 power Aleph naught. That is Aleph 1. And there is no set whose cardinality is strictly between these two. Okay. So next one more. So it has been proved, this has been proved. That is, it is impossible to prove or disprove this particular conjecture within the axioms that we follow. That is the Zermelo-Fraenkel axioms. Whether we use axiom of choice or without using axiom of choice. Whatever way you try, you could not prove or even you could not disprove it also. Okay, that has been proved. So the only thing we have to go is you have to extend your axioms. Okay. So next one. Of course. I don't want to go deep into this because these were that is the original things. You have so many methods, axiomatic method and other things. There were very few axioms. Okay. And you defined something known as cardinal number. And you can see that the set of reals, because in our mindset, both of them are infinite sets. Set of natural numbers, it is an infinite set. Set of reals, infinite set. As infinite sets, we believe that they have the same cardinality. But Cantor proved that the set of reals has greater cardinality than set of natural numbers. Okay, that was proved by Cantor. So one is Aleph naught, the other one is 2 power Aleph naught. That is Aleph 1. Okay. Next one. The Cantor's Aleph ladder is Aleph naught and then Aleph 1, that is 2 power Aleph naught, and then 2 power Aleph 1, that is Aleph 2, and so on. Okay. And people have found out sets with that cardinality. But of course, in between Aleph naught and Aleph 1, we were not able to find out. And that is the continuum hypothesis given by, of course, posed by Hilbert. Okay, next one. Okay. Of course, this is in the original thing. When we had the original axioms, there is an axiom that whole is part. But you can see that when we prove so many things, we have proved that the set of integers and the set of even integers. You could exhibit a one bijection between integers and set of integers and even integers. But we know very well that set of even integers is a proper subset of set of integers. So this axiom, that is a whole can never be equal to its part. That is contradicted. Okay. So originally we started with some axioms. Those axioms, they gave rise to many paradoxes. One is the liar's paradox. So suppose if you have a liar, okay, and the liar says that, he gives that particular statement. What I am now saying is a lie. This is the statement he says. Okay. So suppose if that statement is true, okay, then it must be false, because if it is true means he is saying is what he is saying is a lie. Okay. So then it means that he must have spoken the truth. Okay. And if the statement is false, so what I am now saying is a lie means if it is false means he is saying the truth. So, and then if it is true, that is what I am now saying is a lie, that is true. So again, it must be false because he is not saying a lie. Okay. So if it is true, and we have an intuition that a statement should be either true or false. If it is true, it cannot be false. If it is false, it cannot be true. But here you can see that if the statement is true, then it must be false. And if it is false, it must be true. Okay, next one. You had so many problems. Another one is the Cantas Paradox, found out by Russell. He took that set of all the sets which are not members of themselves. Okay, so a set which is not a member of itself, that is taken as capital R. So the question is whether R is a member of the set. So if R is a member of itself, then by definition it should not be a member of itself. And if it is not a member of itself, then by definition it should be a member of itself. So many such paradoxes. Okay, and then only people started forming that Zermelo-Fraenkel axioms. Okay, next one. Next. Okay, and again you have this Barber's paradox. That is, a barber made a statement. Whoever does not shave himself, the barber would shave. Okay, so the barber said that suppose if I will shave only those persons who do not shave themselves. Now the question is whether the barber will shave himself or not. Okay, so if he shaves for himself, he should not shave for himself. And if he does not shave for himself, he should shave for himself. That is the paradox. Okay. So the insufficiency of the axioms that was felt by Cantor, and so that led to the development of Zermelo-Fraenkel theory, okay, which is what we follow now. And you can see that the importance of this axiom of choice. Okay, that you can see you have proved many theorems using that axiom of choice. That is a very important axiom in this axiomatic set theory. Safina, you can move on to some 2 or 3 slides.
Okay.
Okay. Okay, next one. Leave it here. Okay. So this is Fermat's last theorem. It was a conjecture posed by Fermat, and in the olden number theoretical books, you could see that it is Fermat's last conjecture. So it was posed in the year 1637. And all of you are very familiar with the Pythagoras Theorem. So if I write the Pythagoras Theorem as an equation, I will get 3 numbers, that is x, y and z, satisfying x square plus y square equal to z square. Okay. So I can find 3 positive integers or 3 whole numbers satisfying x square plus y square equal to z square. So the equation x square plus y square equal to z square has a solution in the set of positive integers or positive whole numbers. Okay. Now what Fermat did is, he just increased that n to 3. So if n is strictly greater than 2, he said that you cannot find positive whole numbers x, y, z such that x power n plus y power n equal to z power n. Okay, that was the problem he posed. It was posed in the year 1637, and in the margin he made a small remark. I have a solution of this problem, but the margin is too small to contain it. That was the remark he made there. So people started working on it, and after a century, that is in the year 1770, Euler proved the theorem for n equal to 3. So the equation x cube plus y cube equal to z cube, that does not have solutions in the set of positive whole numbers. That was proved by Euler in 1770. And in 1775, Dirichlet and Legendre, of course, they worked independently, but they proved it for n equal to 4 and 5. And of course, for n equal to 6, you can get it from n equal to 3, because x power 6 can be written as x squared the whole power 3. So you can do it. So 6 is okay. And Lamy proved for n equal to 7. And then a major breakthrough came, because so far people took one number and worked on it. But Kumar could settle for n less than or equal to 100. Okay. So he proved for all n less than or equal to 100, the equation x power n plus y power n equal to z power n has no solutions in positive whole numbers. So the problem remained open. And in 1993, Andrew Wiles, okay, he proved it for all n. And when he proved it, the theorem was known to be true for n less than or equal to 25,000. See, this Andrew Wiles, he looked at this problem when he was 16 in the university notice board, and he felt that one day, because this is again a problem which everyone could understand. So at that time itself, he thought that he should solve that problem one day. And he started working on the problem when he was 40. And he proved the theorem and when he was 47. So he worked for nearly 7 years on the problem. But the very pathetic thing is, he should have been given the Fields Medal. But one criteria for Fields Medal is, because he has given us long-standing open problem, but one criteria for Fields Medal is anyone who is getting that medal should be less than 40. So in that single criteria, he has lost Fields Medal, but of course he has received so many other medals. And you can have another interesting thing is, this appears to be a problem of number theory, and the proof of Andrew Wiles, it runs up to 200 pages. It is available in the net, and you can see that he has used completely all the techniques of algebra. His proofs is an algebraic proof. So what the other mathematicians could not do, that was made possible by Andrew Wiles because of the development in commutative algebra in between years. So he has used all the techniques of commutative algebra in order to solve this number theory problem. Okay. And of course, whenever people present it, some mistakes could have been found out. So when Andrew Wiles presented this proof, there was a flaw that was pointed out by the mathematical community. He started working on it. And at one stage, of course, he couldn't succeed. So he just wanted to leave it off. By that time, his student, Taylor, he joined with him, he encouraged him, and finally the problem was settled. Okay. So entire mathematical community accepted that his proof is right. So Fermat's last conjecture became Fermat's last theorem, and the credit goes to Andrew Wiles. Okay. So next one, ma. And this is a picture of Andrew Wiles. And you can see, you can have a biography of Andrew Wiles in any algebra book, even in that abstract algebra by Gallian. Okay, you have his biography. Next one. So these 6 persons are the doctoral students of Andrew Wiles. And the first one, Manjul Bhargava, he won the Fields Medal. What the guide could not do, the student did. And Manjul Bhargava is again a mathematician of Indian origin. Okay. Next one. This is Manjul Bhargava. Shall I take some 10 more minutes, sir? Sir, is there any time constraint?
No, madam. Okay, madam. Can take.
Okay. Next one, ma. So, of course, this is about Manjul Bhargava. You can move on to the next slide. Okay, again, next one. Next one. Okay. So these are again some 7, each of them is a $1 million problem. You have an institute called CMI, Clay Mathematics Institute, and that listed 7 problems as $1 million problems. So it was listed out in the year 2000, and of these 7, only 1 has been proved. That is the Poincaré conjecture that has been completely settled. The other things, of course, only partial things have been proved. So the complete problem remains open. Okay. I think we can leave off certain things and move on to the important ones. Go to the next one, ma. Okay. Poincaré's conjecture is one that has been solved. So the conjecture was originally posed in this way. That is, if you take don't worry about manifold and other things. Okay, just you can imagine a sphere and a closed something without any holes. You imagine a surface without holes. So if a compact 3-dimensional manifold M3, it has the property that every simple closed curve within the manifold can be deformed continuously to a point. The conjecture says that, does it follow that space is homeomorphic to the sphere? Just imagine an apple and a rubber band put around the apple. If you just pull that rubber band, you can see that finally it will end up in a point. You can just pull it up without taking it up. But the same thing you cannot do in a donut. Okay. So that is the meaning of this conjecture. So it was posed in 1904 by Henry Poincaré. Actually, it is a problem of algebraic topology. Next one, ma. Okay, and later Poincaré himself, instead of taking M3 and then S3, he took up Mn and Sn. Okay, he extended to n dimension. So n equal to 1, it is very trivial because it is a circle. And for n equal to 2, it was proved in 19th century. And in 1961, Stiefel Smale, he proved it for n greater than or equal to 5. And then Michael Fredman, he proved for n equal to 4. So for n greater than or equal to 5 settled. Only thing that was left out is n equal to 3. And in 2002, Gregory Perelman, Iranian mathematician, he proved for n equal to 3. So the conjecture is settled. So all 3 persons are involved in it. So all the 3 are awarded Fields Medal, that is in the year 2010. Okay. But this Gregory Perelman, he has actually succeeded the work done by another mathematician called Hamilton. So the work of Hamilton has been upgraded by this Perelman. So Perelman suggested that Hamilton should also be given the same medal, Fields Medal. But the committee, they gave this medal only to these 3 persons. And another thing is Perelman, he published his paper. He published it in net and he did not publish it in any mathematical journal. And so this person, he refused to receive that medal. Okay, he rejected. In fact, the only one who had rejected the medal is this Gregory Perelman. Also, he was given that $1 million by that Clay Mathematics Institute. That also he refused. Next one, ma. Okay, next one, next. Of course, this you can leave because it is, of course, you couldn't easily understand about it. You can just leave it off. Next one. This is again, Hodge conjecture is a problem of algebraic geometry. Okay, next one. This is 4-color theorem. Actually, in graph theory, you would have studied the 5-color theorem. That is, every planar graph could be colored with 5 colors. And the 4-color theorem says that it could be colored with 4 colors. That is, if you color a map such that 2 countries with common boundary should not have the same color, it is enough if you have 4 colors to color the entire map. That is 4-color theorem. So it remained open. It was posed in the year 1852. And 2 computer science persons, Apple and Haken, they solved it. But it is not a logical proof. It is only a proof based on computers. Once you give anything, it will be giving you the output, coloring it in all possible ways and only using 4 colors. So it is not a conjecture. It is not a conjecture now. It has been proved, but not using the logical argument which we use for a 5-color theorem. So it is still, the mathematical proof is still open. You have proved using computers. That's all. Okay. So of course, if whatever map you give, you can color it using 4 colors. Next one, ma. Okay. So this is P and NP. P means the class of problems for which you have a polynomial time algorithm. Okay. And NP is given an instance, the checking whether it is a solution or not. That can be done in polynomial time. But so far you don't have any algorithm which is of polynomial time algorithm to solve that problem. That is the class NP. So one is the class of problems having polynomial time algorithms, that is P. Another one is the class of problems. So far, no polynomial time algorithm is available, but checking the solution can be done in polynomial time, that is NP. And Cook posed this question, whether P equal to NP. Okay. So to understand this class NP, suppose if we go to a marriage, okay, and we don't know anyone, maybe it is a friend's marriage and we don't know anyone in there. And suppose if your friend says that, see, look at that person with that green sari. She studied with us, means just you can look at that particular girl and then you have someone known to you. You can identify whether she has studied with you or not. But suppose if that particular girl has not been shown to you, what you have to do is you have to check the entire crowd. and see whether you have anyone who is known to you. That is the difference. Here you are doing only the checking, you are not finding. Suppose if I ask you, I give you a number and I say that this number is a factor of this, immediately you can divide and check whether it is a factor or not. But if I ask you to find a factor, then you have to work a lot. That is the difference between P and NP. Okay. And this is again a open problem. Next one, Max. Okay, and this actually, this is people say that this is a gift of mathematics to computer science, because as it is with respect to that algorithms and complexity, so much of theory has been developed in computer science because of this problem. You have a class of NP complete problems, NP hard problems. So that is saying that it is a boon from mathematics to computer science, and the problem is still open. And this is again a $1 million problem. Next one. Okay. Actually, this is a rough diagram to explain about these two problems. The first structure is when P is not equal to NP. We don't know whether P and NP are equal. So if P is not equal to NP, inside NP, I have a NP complete list. That is, there I have some list of problems, and any problem in that list could be reduced into another problem. And then I have NP hard problems, for which so far the verification itself could not be done in polynomial time. That is NP hard problems. So the first one will be the structure if P is not equal to NP, and the second one will be the structure if P is equal to NP. Okay. But of course, it is an open problem. Next one. This is the Riemann hypothesis. That is about the roots of the Riemann zeta function. Actually, Ramanujan has done a lot of work in Riemann zeta function, but this hypothesis, this conjecture is not settled. Next, ma. Okay, this again, of course, you can just leave it off. It's about Lie algebra. You can go to the next one. Okay, this is a Reconstruction Conjecture. It is a problem of graph theory. Okay, it is again a long-standing open problem, and only very few people work on this conjecture. What you see that you take a graph, delete one vertex. So delete vertices one by one. Take the vertex deleted subgraphs. Okay. So the collection of all vertex deleted subgraphs, that is called as deck, and each element is called as a chord. And the conjecture says that if two graphs have the same deck, then of course they are said to be hypomorphic. And the conjecture says that every graph can be reconstructed uniquely from the deck. So that was the conjecture. It is still open. So as the original conjecture seemed to be very difficult, Harari, he reformed it as set reconstruction conjecture, and then another variation is edge reconstruction conjecture. But still, of course, you can see that it is an open problem. But the condition on at least 3 vertices, that is very essential, because if you take 2 vertices, there are 2 graphs in 2 vertices. One is that 2K2, the 2 vertices. Another one is an edge. And you can see that for these 2 graphs, the deck is the same. You have just one vertex. But you cannot reconstruct the original graph. If you reconstruct, in one case, you will get 2K2. In one case, you will get edge. Okay, so it is not unique. So it is not true for n equal to 2. So you have to take at least 3 vertices. So this is an open problem. Safina, you can, it is 4:14. So you can move on to the last slide, just before last slide.
Okay.
Okay. Just before that. Okay. So just as I started with tribute to the 2 mathematicians who received the Abel's Prize, this is a tribute to the first woman who received Fields Medal. Okay. That is an Iranian mathematician. And in fact, she is the only woman who has received Fields Medal, Mariam Mirzakhani. But the very unfortunate thing is she died at the age of 40. So she received Fields Medal in 2014 for her work in dynamics and also the geometry of Riemann surfaces and also their moduli spaces. So she died in 2017, and her date of birth is 12th May 1977. So in the ICM 2018, which was conducted in Rio de Janeiro, it was decided that that particular date, 12th May, that was fixed as day for celebrating women in mathematics, okay, in memory of Mariam Mirzakani. I think I can end up with this, and if I have any questions, you can just ask. So thank you. And thank you, Safina, for sharing. Thank you.
Thank you, ma'am. Shall I stop the sharing now?
Yeah, you can stop.
Okay, ma'am.
Thank you.
Participants, please do raise your questions. You can post it in the YouTube chat box. I don't see any questions. Nagarajan, sir?
Did you have the same problem yesterday in sharing?
No, ma'am. There was no problem yesterday.
Oh, so I couldn't understand why you get it like this.
Maybe the internet connection is weak.
Uh-huh.
Large files may not be
Oh,
transferred.
okay.
Madam, it is very interesting.
Thank you, sir. Thank you, sir.
You just described all the history of medals and the Fields Medal and the Apples, etc. And nobody knows it. It's especially youngsters, they do not know it. What are the Nobel equivalent Nobel prizes, etc.
Okay,
And
sir.
the facting and the conjecture, and you were started from the conjectures and open problem, and you were finished in a nice way. Thank you, ma'am. Thank you very much.
Thank
And it
you,
is
sir.
very interesting from the beginning to last slide. Very interesting. Really very interesting.
Okay, sir. Thank you, sir. Thank you. And
So
thank
shall
you for
I,
giving me this opportunity, ma. Thank you.
Thank you.
shall I propose the vote of thanks, sir? Nagarajan, sir? Nagarajan, sir, can you hear me?
Yes, ma'am. We can breathe.
May I propose the vote of thanks?
Yes. You can
Yes, sir.
proceed.
It is an honor to propose the vote of thanks. First, I thank our Honorable Secretary, Thri APCV Chokkalingam, and our respectable Principal, Dr. C. Veerabagu, who are the pillars of every event in our college. Next, I express my thanks to our beloved HOD, Dr. A. Nagarajan, and the Organizing Secretary, Dr. S. Jackson, and all my colleagues for this program. Next, on behalf of everyone, I express my deepest gratitude to our honorable and respectable resource person, Professor Dr. R. Kala of the Mathematics Department, Manoன்மணியம் Sundarnad University. Thank you, ma'am, for your enlightening talk on various conjectures and open problems. You gave us insight as to how we ought to choose a problem for research and how we ought not to. So we take it from your talk today that we should not get caught in easy, understandable nature of open problems, and but nevertheless try to find weaker or alternate versions of these problems which might be solvable. The flow of axiom, paradoxes, and all conjectures are very beautiful. Actually, it was very interesting. Thank you. I hope all of us gathered here have gained understanding about various open problems and conjectures you gave us. On behalf of, last but not least, I thank all the participants who are present for this program, without whom this program would not be a success. Thank you, one and all. Thank you, ma'am, once again.
Thank you, ma. Thank you.
Thank you, ma'am.
Thanks, sir.
Thank you, respected Kala, ma'am.
Thanks,
Thank
sir.
you.
Thank you, sir.
Thank you, Safina ma'am. Ma'am, Safina ma'am, kindly share the feedback link
Yes,
in the Google Meet chat box and also in the YouTube chat box, please.
just a minute. So participants, I'll
Thank
share
you.
the feedback link now. You can fill it within 20 minutes after I post it. Thank you.
Shall I leave, sir? Yes, sir.
Okay, madam. Okay, ma'am. Thank you.
Thank you, sir. Thank you, sir.
Thank you.
Thank you. Thank you.
மேடம் ரொம்ப இன்ட்ரெஸ்டிங்கா இருந்துச்சு மேடம். இந்த இப்போ உள்ள அந்த கண்டெக்சர் இது மட்டும் இல்லாம அந்த ஹிஸ்டரி சொல்லும் பொழுது அது மட்டும் இல்லாம அவங்களுக்கு ஸ்லைடு பை ஸ்லைடே வந்து ஒரு கம்ப்ளீட் ஃபாலோ அப் இருந்துகிட்டே தான் இருந்துச்சு. எல்லாருக்கும் நல்லா கம்ப்ளீட்டா அந்த நல்லா இருந்தது. இந்த சீக்வன்ஸ் ஆஃப் இது ரொம்ப நல்லா இருந்தது. அந்த அதுக்கப்புறம் எல்லாமே ஆமால அது சில சமயத்துல நம்ம ஒன்றும் கண்ட்ரோல் இல்லை மேடம். சில சமயம் வந்து ஹேப்பன்ஸ் லைக் தட். அதனால இவங்க ஜாக்சன் இந்த மாதிரி ஆட்கள் இருக்கிறதுனால தான் நம்மளால முடியுது, இந்த மாதிரிலாம் செய்ய முடியுது. இல்லைன்னா இது எங்களுக்குலாம் கஷ்டம் அது. அதனால சரி சொல்லிட்டு நல்லா இருந்துச்சு மேடம். இன்ட்ரெஸ்டிங்கா இருந்துச்சு. கிராஃப் தியரினா நம்ம ஒரு பர்டிகுலர் கிளாஸ் ஆஃப் பீப்புளுக்கு மட்டும் ரெஸ்ட்ரிக்ட் பண்ணிப்போம். இது எந்த கிளாஸ் ஆஃப் பீப்புளா இருந்தாலும் சரி அந்த இது ரொம்ப இன்ட்ரெஸ்டிங்கா இருந்துச்சு. இதுவும் ரொம்ப அந்த ஆஃப்டர் அந்த இது லாக்டவுனுக்கு அப்புறம் வந்து இந்த மாதிரி விஷயங்கள்லாம் நிறைய இருக்கிறது வந்து அவங்களுக்கும் தெரியும்ல. ஸ்டூடெண்ட்ஸுக்கும் அவங்க ஷேர் பண்ணுவாங்க. நல்லா இன்ட்ரெஸ்டிங்கா இருந்துச்சு மேடம். தேங்க்யூ மேடம். தேங்க்யூ.
Participants, I've shared the feedback link. You can check it. Thank you. Nagarajan sir, can we wind the program?
Okay, ma'am.
Thank you, sir. Thank you, everyone. You can leave the program now.
ஃபில் பண்ணிருப்பாங்கல்ல ஃபீட்பேக்
ஃபீட்பேக் அனுப்பிட்டேன் சார். கூகுள்
இல்ல
மீட்ல
ஃபில் பண்ணிருப்பாங்க லைன் உங்களுக்கு கிடைச்சிருக்கும்ல. ரைட், ஓகே.
ஆமா சார். இத ஓபனா வச்சிருக்கேன். ஒரு 5 minutes ஓபனா வச்சிருக்கேன் சார்.
ரைட், ஓகே.
ஆல் ரைட்.